We have just experienced in the last 4 years the hottest temperatures. 2016, 2017, 2015, and this last year, 2018, is the fourth highest. Of course, this was a super El Nino here. There was also a very strong El Nino here. The temperature is rising since about 1970 here at 0.17 degrees Celsius per decade. This is the global surface temperature. Okay, it's actually hotter on land than it is in the above the ocean. Land temperatures have risen 2.7 times faster than the ocean temperatures. So in this video, I'm going to discuss these factors and also how the temperature is varying through the seasons, also comparing land and ocean temperatures, how we're setting records, and what we can expect in the near future. If you hear the occasional dripping sound in this video, I have a couple buckets in this room because of these freeze, thaw cycles. We were in a thaw cycle, and I guess I have a some problem with leak in this room. And if you hear a scurrying around, it's not my cats. It's I've got some squirrels up in the above the ceiling, I think, here, and maybe they've chewed a hole in, and it's contributing to the leak. So thank you, climate change. It affects everybody. Okay, so getting back to global average temperatures. First, I'll go to my website. So this is my website. I just posted a couple videos recently. Antarctic needs a dentist. The second video is more technical than the first video. It's on all the details of the huge cavity that was found in Antarctica. Okay, so please have a look check out my website if you haven't, and please consider donating to support my work at PayPal. I'm an independent climate scientist, so this is the only funding that I get is through you, through your donations. You keep me going, and I thank you from the bottom of my heart for that. This is my Twitter feed here at Paul H. Beckwith, and basically there's this plot here, which I just showed you. Land temperatures have warmed nearly 2 times as fast as ocean surface temperatures. Okay, this is not actually an accurate statement. It's 2.7 times as fast. If you take this slope and you take this slope, these are the endpoints, 1.6 and 0.8. That's a 2 times difference. But you need to take the slope of the curve to get the rate of warming, and they both start. They don't start at 0. So the actual slopes vary by a factor of 2.7 times. This is a paper, a summary of the temperatures by James Hansen at Columbia, and that's what I'll be talking about. So first of all, the data is from GISS, the Goddard Institute for Space Studies. Okay, so you can just Google the GISS site and have a look at it, and they have all kinds of graphs and maps and different station data and different ways of depicting that data. Also, there's a page by one of the authors where this is posted, updating the climate science. What path is the real world following? Makiko. If you Google that, you can find this. There's links to Storms of My Grandchildren, the classic book by Hansen. Global Temperatures is this particular paper I'm going to show you. I just want to point out quickly the El Nino record has been updated. This is the big 2015-2016 El Nino. This is the 98 one. This is where we are right now. So I'll talk about, whether there's still a chance that we'll have a weak El Nino. It's unlikely to be as strong as the one a few years ago. So I just wanted to point out this website. There's information, and it gives you when it's last modified, which is useful to see if you can get to get the latest current data. Now this is the paper that I want to talk about. It was just released. This article was just released February 6th. Global temperature in 2018 and beyond. So basically the year 2018 was the fourth highest, as I pointed out. The 2018 global temperature was plus 1.1 degrees C, warmer than the 1880 to 1920 base period. Okay, so basically, so here I showed you those 4 years. Now, the El Nino was most powerful in 2015, but there's about a 3 to 4 month lag. You know, when there's an El Nino, the heat has to be released from the ocean, go up in the atmosphere. There's about a 4 to 5 month lag. So although the El Nino was strongest in 2015, the temperature record was highest in 2016, and this was the year after when it started to dissipate, 2017. So these 3 points are related to that El Nino, and this point is this year, 2018, which is the 4th highest. And again, 0.17 degrees Celsius per decade, that's the slope of this line. That's from 1970 to 2018 data. Okay, so how does that temperature break down on a map? How is it distributed spatially across the Earth? So this is 2015, the 3rd warmest year. You can see the strong El Nino here, strong temperatures over the Atlantic, just west of South America here. This is a classic El Nino figure. 2016 was the warmest year, and you can see that the El Nino has decreased in strength, and this is because of the lag. For this temperature to be expressed in the air, there's a 3 to 4 month lag. So 2016 was the warmest year. It was a full degree above the average temperature between 1951 and 1980, the climatological mean. Now, the reason why 1951 to 1980 was chosen is because there's lots of data. So for these maps to have, you know, if we chose earlier baselines, there'd be lots of data missing, gaps in these maps. So that's the reason. 2017 was the 2nd warmest year, 2018 the 4th warmest. So this is relative to this average 1 degree. Now, remember in 2018 in the introduction I said we were 1.1 degrees Celsius above the 1880 to 1920 average. So 1.1 minus 0.83 is 0.27. So the difference between this baseline and the 1880 to 1920 baseline is 0.27. So we need to add 0.27. So we're in 2016, the warmest year, we were 1.27 degrees Celsius warmer than the 1880 to 1920 baseline. Now, they're calling that pre-industrial, but the real pre-industrial is 1750. So to go from 1750 to the 1880 to 1920 baseline, you need to add 0.2 or 0.3 degrees. So adding those numbers to 1.27 gives you 1.47 to 1.57 degrees Celsius in 2016 relative to 1750, and that's already bracketing. That's basically at the 1.5 degree aspirational target above pre-industrial that's been discussed in Paris. The original number was 2 degrees Celsius above pre-industrial. So for the year 2016, aided by a very powerful El Nino, we exceeded the 1.5 degree aspirational target already. A paper came out recently talking about how we're likely to break that number in about 4 or 5 years, even without an El Nino. Okay, now global land area has warmed about twice as much as global ocean, as shown in figure 3. Now, I said it's not about twice as much, it's 2.7 times as much. So how did I get at that? Well, these are the endpoint temperatures, 1.6 and 0.8. But you really want the slope of this curve. So you need to take 1.6 minus where it starts at about 0.4, divide by, it starts at 1975, divide by the years, 25 years plus another, they're going to 2020, that's 45 years, and you get the slope of this curve. And the slope of this curve is 0.27 degrees Celsius per decade. Do the same thing. This doesn't go through 0, right? Get the slope of this curve, and it's 0.10 degrees Celsius per decade. So you need to compare the rate of change of land warming versus the rate of change of the surface of the ocean warming is 0.27 over 0.10, which is 2.7 times faster. So this is basically a very juvenile, they didn't think very carefully when they came up with this saying. Both in this paper and in the tweet, as I pointed out earlier, the fact is 2.7 times faster. Okay, but the point is we're getting tremendous warming over the land, and of course, as you go higher north to higher latitudes, we're getting tremendous warming in the polar regions. So the polar land regions are, they have both effects. Huge warming because it's land surface and also because it's a high latitude when you combine those two figures. Now there is seasonal variation here. So this is in 2018. The winter, spring, summer, and fall. And what you can see, I'd like to point out the fall. So the overall year, right, was the overall year was 0.83. If you break it down by seasons, there's some variation about that, with the least warming in the summer and the most warming in the spring here and winter, okay, and fall. But what you can see is, look at the fall numbers, September, October, November. Look at the only cold area is over North America. And this has continued into January and February of 1919 with the breakout of the collapse of the jet streams, the breakout of the polar vortex coming down over this region. So when people say, oh, it's very cold, where's global warming, just show them this plot here. North America was the only place that was colder. Everywhere else was warmer. The prospects of an El Nino. So this is the temperature anomaly for the El Nino. This is a very powerful 2015 El Nino going into 2016, and this is what we have now. So it remains to be seen in the next few months whether an El Nino will develop, but it doesn't look like it will be anywhere near as powerful as the previous one, which brought us to temperature records. Now, this is a key plot which I'd like to show you, the total solar irradiance. So this is what the sun is doing. This is the energy that is being put out by the sun that's incident on the Earth. And you can see this is the number of sunspots. Okay, so you can see that the energy is tracking the sunspots, the number of sunspots. And what you can see is that in the 2015-2016 El Nino, we were at a peak of irradiance coming from the sun, okay, and that would have contributed to help make that El Nino even more stronger. Now, what you can see is we're going into a minimum here, but the key thing is the sun is putting out, over this cycle, it's putting out 1360.5 watts per square meter at the lower part of the cycle, and almost 1362 watts per square meter at the higher part of the cycle. That's only a variation of 1.5 watts per square meter, and if you divide that number by the total to get the percentage of change, it's very, very small. In fact, it's 1.5 watts per square meter, divide it by the mean, okay, 1361.25 roughly, and you get 0.1% roughly, 0.1%. Okay, so the solar activity, the sun output is only changing 0.1% during the sunspot cycle. Okay, and that is although that's a measurable impact. It's ridiculous, these claims that we're going into a grand solar minimum and it's affecting everything. Those claims are just absurd. I mean, the sun this is data from the sun, and the variation is tiny. If you average over the Earth's surface, the absorbed solar energy is 240 watts per square meter. The full amplitude of the measured solar variability is therefore only 0.1% of this, or slightly above, which is 0.25 watts per square meter variation, which is very, very small compared to the greenhouse gas effect. Okay, so basically, in summary, we continue to set records for temperature. It's warming much, much quicker over the land and also at the poles.